So, now, I guess, like some of the other presenters, especially Oliver, who I was also a little bit thrown for a loop about what it actually means to when you talk about introspective methods. The way I've approached this in this presentation is that introspection is about looking into why, more generally, just why a particular decision is being made. So I've kind of equated an agent's introspection with dealing with the same problems and requiring the same type of information as if me as a human, be it a human as a user, a human as a developer, a human as a domain expert, a human as an analyst, looking at the agent and trying to figure out where a particular decision came from for a particular purpose. Both the purpose of the agent as well as the purpose of why I'm looking at it. So that's the take on introspection that I've used, and that neatly dovetails then with a field of artificial intelligence that's gaining a bit of prominence, especially now, even though it's actually been around for a long time, called explainable artificial intelligence. Broadly speaking, it's an answer to the trend that's been happening over the past decade or so, where a lot of the decision-making, especially the more complex decision-making being made by these autonomous agents, is moving from planners and sort of traditional AI type things, which, while not being easily explainable, at least we have some idea of how they work, and we've kind of coded them up to do things, and moved to models which are induced from data of various sorts and other forms of information, but that encode their representations in a way that is even less meaningful to us humans as some of the previous representations. So, the case for explainable AI, and I've lifted this from Dave Gunning's sort of program at DARPA, the DARPA Explainable AI program. Who is familiar with DARPA XAI from last year? Okay. And part of that involves a very sort of human aspect of this. This is an AI agent working with a human, saying explainable AI will be essential if users are to understand, appropriately trust, and effectively manage this incoming generation of artificially intelligent partners. Now, that sounds all well and good and reasonable, but that in and of itself already speaks to several different uses of this explanation, right? Are we trying to use the agent? Are we trying to understand it? Are we trying to either trust the agent or make the agent easier for a user to trust and manage? Okay, so, and it gets further, right? So, some questions that you may ask of an agent. Why did you do that? Why did you fail? How can I trust you? How do I correct an error? One of the things that I noticed talking about getting explanations out of a lot of these systems is that a lot of practitioners, especially those of artificial intelligence, and especially those that have come from very much the development of the techniques themselves, will focus on one or two or several of these questions. But the ones who come at this problem from the application side, from I have a problem that I want to solve and I have a variety of different users to keep happy, what technique do I use? When it's developed from the user perspective, from the application perspective, it seems that you get a much broader set of semantics with which to talk about this. So the goal of this talk is to propose a set of semantics developed from the application, from the user perspective, that allows us to talk about what types of machine learning techniques have the capabilities to solve various explanation problems. And to me, it doesn't matter whether that explanation problem, whether the purpose of that explanation is to generate something for a human, or whether the purpose of that explanation is to generate something for the agent's own introspection. And actually, I will argue a bit later on that actually there might not even be a difference between the two, insofar as the agent needs to perform its own introspection in order to form an argument that it can then present to a user. Okay? What I will not cover in this, which is what a lot of people sort of immediately jump to when they think about explanation, is issues of HRI, HSI, HCI, HMI, whatever the thing you want to call the agent working with the human. So how do I present this to the human? And I'm not really going to talk so much about things like, the cognitive science aspects of this. I'm a little, because I mean, a lot of people have been working in that field. A lot of people have talked about how do you generate an explanation that a human is going to like, that's going to make them feel warm and fuzzy, that they're going to understand, levels of granularity, and so on. Very, very important. But those formulations, those semantics, those terms, usually make the assumption that the underlying information necessary to generate those explanations already exist, which might be true in classical AI, in a lot of planning, sometimes, mostly, but is definitely becoming not so much the case with a lot of machine learning. So, of course, the goal after all of this is to have answers to these, and in fact, I will actually, I'll be so bold as to propose that there's actually a few more questions that we need to have these systems be able to answer. Particularly, I can see how you came to your decision, I know how to fix you, and also I can learn something from you. So, and of course, the reason why I think we need to have a separate set of semantics around this is because I think the fact that we have different applications, different users, and different explanations is something that is not particularly well tackled with the with how we talk about explainability at the moment. And of course, after all, the type of explanations you might expect out of the robot watering your plants, and you're trying to figure out, well, why does it always water the kumquat tree before it waters the apricot? Is possibly a little bit different to the explanation that that a developer at JPL will want out of the rover if it says, well, wait a minute, why did the rover take that path and not this one? Which is, again, different to the explanation that a regulator might want out of Waymo if something happens and they're trying to figure out how to make sure it doesn't happen again. And the same with if you start having robots wielding knives and cutting into people. I'd also argue it's also kind of useful in general because if we want to prevent the robot apocalypse, it kind of helps if we know what they're thinking. Okay. Oh, good, I got one chuckle out of that. I'm happy. Of course, talking about regulators, of course, the other reason why this is becoming important is because we may not have a choice about whether we think about this or not. Now, who here knows about the GDPR? Okay, so this was actually, I was actually giving an earlier version of this presentation at ITCHCAI recently in Melbourne, and this was some kind of topical. The European Union has put forth this general data protection regulation. It's significant because it's a regulation. This thing comes into effect in May next year, whether the countries in the EU do anything or not. And while most of it talks about data privacy, part of it involves something called this right of citizens to receive an explanation. Now, this, of course, is mostly talking about, a company, uses a data mining thing involving some deep learning thing which decides this person has this premium for their insurance versus, this person is in another premium bucket for their insurance. But the point that I want to make is that as embodied systems, take hold and become more prominent and start making more of these decisions, there's already a precedent that regulators know what we're doing, they know what we're up to, and they want to get in on the act and make sure that that various regulations and protections are enforced. So, once the implications of your self-driving cars become more important, I can imagine similar things coming up on the horizon. So, and actually I'm going to come back to this example because I want to make sure I get to the next bit and I'll come back to that. Okay, so this is a proposal for yet another rough categorization of explanations. And I say yet another because, of course, it's not like we don't have enough of them already. But as I stress, the point about this categorization is as a tool to talk about the requirements of explanation and match it up with machine learning techniques and meta techniques on the top of those that can answer those problems. So we propose splitting this along two dimensions, one based on the requirements, be they for teaching, introspective tracing, introspective informative, post-hoc and execution, or based on depth. And when I talk about depth here, I'm not talking about what some people in explanation call granularity, right? Like, one example, might be, how does a helicopter fly? Well, this thing spins around and these things generate lift versus, the helicopter has two aerofoils or three aerofoils, there's a swash plate, blah, 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 right? So that's not what I'm talking about. Okay, so what are all these? So the first one, and this is actually one that I find a lot of people, especially those who are talking about explanations from the perspective of the underlying techniques, tend to forget about, and that is that of teaching explanations. This is explanations that teach us something new about the problem domain. Actually, those of you who are more familiar with the expert system side of the house will already be familiar with this. Here, so we induce a model with data and other things that we might feed into it, background knowledge or whatever, and the goal may not even be to run it. The goal may not even be to make decisions. The goal is for the machine learning technique, for the agent, for the whatever the case may be, to, in a sense, summarize, aggregate all of the knowledge that it has gained, and then explain to us what it's doing and why it's doing it, or what it can do, or why it can do it, or so on. Then there is what I call introspective tracing explanations. This is, to some level of abstraction, how an agent actually came up with a decision. So, now this doesn't necessarily mean the individual instructions that it executed. In fact, that's a different category. This is tracing through exactly how a decision was come about so that you know, for instance, why a particular error came about, what's involved in it, in what other circumstances it might make this error, and how to fix it. So an example of where an introspective tracing explanation might be useful. Let's say at some point an autonomous car runs over a pedestrian. Given the statistics of how many cars there will be in the future, regardless of who's at fault, it's going to happen. Unfortunate as it is. And let's say it's traced down to the vision system on the camera didn't see the pedestrian, for whatever reason. How is the manufacturer or the developer of that algorithm going to be able to convince the regulators, a coroner, whoever the case may be, that they've fixed the problem, or that they know what the problem is, they know what other situations the vehicle will make a similar error, and that they fixed it so that it won't happen again? Okay, so that's the type of explanation here. And on a simpler level, let's say an AI agent makes a decision and you disagree with it. This will give you the type of information that will be able to either convince you that you're wrong and that the agent is correct, or that it lets you know unequivocally that the agent is wrong and that you're correct, and perhaps how to solve it. Right? One of the sort of discussions that I hear is that there's this trade-off between expressive power of the machine learning technique and how explainable it is. right? And there's this trade-off, if you want to have explainability, you've got to trade off some predictive accuracy. And I would propose the question of, what would you prefer? Would you prefer an agent that is right 95% of the time, but where it comes up with a decision that you don't agree with, you're not really sure who's correct? Or would you prefer an agent that is correct 90% of the time, but where you and the agent disagree, you can be pretty sure who's correct? This doesn't necessarily mean, by the way, that you're 100% of the time correct either, right? There's still a failure rate in there. So it's not a cut and dried answer, and it depends on your application. But it's a question, right, that I think needs to be asked when you think about this trade-off between explainability versus predictive accuracy. Is actually sometimes we can afford to have a little bit less predictive accuracy in collaborative systems, or at least systems that can talk to a human, if the system makes it better, more possible, especially once you add additional introspective techniques, however we define them, that allow the human and the agent as a team to get better performance. So, next category, introspective informative explanations. So, this is one step back from tracing. You don't necessarily have insight to every single reason as to why the agent made a particular decision, but you've got a bit of information there, right? It's, you might not, let's say you have some kind of meta model, or some of these sort of combined models where you can sort of trace it partway down and then it ends up in a black box somewhere. But you're fairly certain what comes out of the black box, is vaguely correct. Things like that. So this is kind of a halfway thing. And then we get to one which I think can be a little bit controversial, or at least more so than what I've been talking about, and that is what I'm proposing to call a post hoc explanation. What this means is you have an agent and it's made a decision, or rather you have a subsystem of the agent that's made a decision, and you then induce an explanation that matches that decision. Now, this sort of parallel system that makes this explanation could be valid across the entire space that the agent works in. It could be valid over the area that the agent mostly works in, or it could be something that has to be induced on a per decision basis, right? I misuse terminology when I sometimes refer to this as it's like you're linearizing the decision, right? You're linearizing the explanation. You have an explanation that is valid in the local area of a decision, but as you move away from it, the accuracy of that explanation drops off. Now, those of you who understand behavioral cloning, which is one of the techniques that I was quite heavily involved with, will have realized at this point that actually the expert system, the inducing of explanations based on expert data, is a post hoc explanation. Okay? You're treating the expert as a black box. Where I'd argue the difference is that it's a post hoc explanation if you're trying to use the model to explain the expert, whereas it's an introspective tracing explanation if you then run that parallel system and use it to generate the decisions instead of the expert. Then there's, of course, there is some arguments of, okay, well, let's say we can develop systems that can explain neural networks by inducing these parallel systems, and I'd say, well, yes, that's terrific, especially if you end up using it to generate the data that these parallel systems can then learn from and get even better performance. But I will ask the question, though, is would a post hoc explanation, be it for feeding into introspection or for feeding into something that you're going to give to a user, would that satisfy the GDPR? Would that satisfy the regulator who you need to convince that your car is safe to drive after you've fixed it? I don't know. But that, I think, is an important question and one that needs to be considered in among all the other ones. And then there is what the type of explanation that I alluded to earlier, which I'm calling execution explanation, and that's literally how the computer executes the program, right? This is the memory dump. This is the, I executed this instruction and then this instruction and this instruction, which for your average user is probably completely pointless, right? You can't understand this. But then again, if you're the JPL engineer and you're trying to figure out why your Mars rover proposed going down this way and not that way, you're sufficiently invested that this type of explanation is actually useful in combination with the rest of them. Now we talk, and then of course, all of these have depth issues, so we can talk about techniques which will give us information about which attributes were used and nothing more. For example, some of the work on peering into some of these black boxes of, say, deep learning, neural nets and the like, can actually start doing some of these attribute-only explanations, right? I came to this decision, and most of it was due to this set of attributes over here and not this over there. The next level, I would argue, is something that I'm calling attribute use. That is, how the attributes themselves, what were the boundaries? Where were how were these attributes put together and used in combination? Decision trees, of course, are an obvious example because they have very clear splits. But of course, other techniques are also able to give these explanations. Now, the thing about these explanations is that they go as far as, here is how I use the model that I have in me to come to this decision. Which might be enough. It might be enough for the GDPR. One thing that seems to be a lot more difficult and seems to, I think, be not quite so prominent in people's consciousness is what I'm calling model generation. That is, how did the model come about in the first place? Let's say I have my autonomous vehicle, and the example that I'll go back to later on is about a vehicle which is driving over rough terrain and has learned from data how the actions that it's supposed to take in order to get over rough terrain to get to its goal. And let's say it turns left, and part of the reason why it turned left is because this area in front of me was 30 centimeters higher than the body of the robot, and I know that if it's 30 centimeters higher than me, I can't get over it. Now, okay, so that's nice and that's introspective and that tells the user something, but the user might scratch his head and think, okay, well, your wheels are a meter big, a meter in diameter. Of course you can get over that. What's going wrong here? Something's up. I want to know where this 30 centimeters comes from. It'd be kind of nice if the system can then say, okay, well, in my training data, here is all the data on either side of this split, and look, if I put the split at 30 centimeters, it needs to separate this data from this data. And because of this, I think that I can't do that. And then, the developer at this point, it's not the user anymore, the developer who's troubleshooting this can look at that data and say, that's interesting. Wait, no, it was all collected on that day that we had that sensor failure. And, that data slipped through. Okay, I know why you made that mistake. Let's get rid of that data and, train a patch over that part of the model, right? It'd be kind of nice to have that level of ability to introspect into the model, to have the introspection of the model help us. I'm not dependent. I don't want to get too hung up about that side of the semantics because I think it's more important to figure out how we can make these systems work. The point of the matter is, I think being able to consider explanations at these different levels is very important, and as far as I've been able to tell, there hasn't really been developed a set of semantics that lets us consider all of these, that gets all of these different machine learning techniques in the same space to talk about them. So, okay. And to give you, let me get back to, and this is me being silly with Prezi. Here's the example that some of the work that I did. This was actually a while ago now, where we have this particular robot running over this particular terrain. Yes, the terrain is not particularly difficult. The whole point about this, though, is that this terrain is in that gap between the types of terrain that this robot can get over using a general motion model, albeit a particularly robust one, and the type of terrain that this robot can't get over at all. Okay, it's in that gap where you can't use a predefined motion model, but you can still get over it if you really think really hard and get over it. And as a human, you get it, as a human expert driving over this, you get over it about 50, 60, 70% of the time. Okay, it's hard. And our attributes flying into this system are some attributes about the navigation corridor that it has to stick to, and some information about the terrain in front of the robot. And out of that, we run the robot over this terrain. We have a human drive the robot back and forth, back and forth, back and forth. And actually, we also, later on, we do some simulation trials, and we have the robot drive itself back and forth, back and forth, back and forth, and we actually use a planner that's not deterministic, but we can do the simulation to get some perfect traces out of this. And we induce a tree that looks like this. Now, what we've done here is just so that it all fits on the slide, and we can talk about this in a few seconds. We've told the tree to prune extremely aggressively. Okay, so this hasn't been artificially cut off; it's just been pruned very heavily. If the full tree goes to pages and pages and pages, which, by the way, is another question about explainability, is whether it makes any sense. So, one of the nice things about this is, of course, let's say we want to talk about that leaf node. Well, here is a dialogue that we might be able to carry out with the robot. Now, I should point out, I'm not going into natural language processing, natural language dialogue, blah, 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 blah. I'm purely interested in, can we even extract this information out of the underlying system to begin with? Okay? And this entire dialogue also appears in the poster that I've got, so I'm not going to go into it. But the point is, regardless of whether the user of the explanation is a human user or whether it's introspection in order to improve itself or to present to a user, I think it's actually kind of important that we can get this level of information out. Dum-de-dum-de-dum-dum-de-dum. Okay. So, but anyway, so now that we've sort of talked about that, we can come back to these different applications and talk about how, these different levels of explanation can mean different things, okay? You can now kind of think about a post hoc explanation is perfectly fine if you're trying to figure out how to water the plants, or you're trying to do a system that explains how a particular thing in the world works, where there's no guarantee that the agent's own model is a better representation than the world anyway, right? There are certainly plenty of situations where the world works a certain way. There's no knowing whether decision trees, SVMs, neural networks are a better representation. All you care about is you want an explanation. Whereas if you're trying to talk to the coroner, you might want something a little more grounded in the actual decisions. Anyway, I'm going to finish there, so I believe that means we have 10 minutes to discuss, right? Yes? Okay, cool. So I'm going to leave it there for now. I thank you for your attention, and I'm willing to have an argument now. Or debate. Let's be simple about this. Yes.
Yeah, I think it's really nice. But I was wondering about what you do with uncertainty and risk.
Yes.
Because I think that's something also part of explainability, which maybe in a lot of situations you don't think you can explain.
Yes.
And another thing about, isn't it fundamentally impossible to explain deep learning decision maker explicitly? Because if you could do that, then you could replace that with your explicit explanation of what the decision was based on. So I have a couple of there are a couple of answers to that. So the first one, we're talking about the uncertainty side, and actually this feeds into the previous talk that you want to know if the system is certain about something, right? So I would actually argue that that's part of this. That's part of your what we need these systems to do. And you can actually see in this example here, this actually is particularly correct 61% of the time. Blah blah blah. There will be additional statistics you can get out of these systems, especially ones that store a lot of these statistics about the data that came through it. In terms of, can you actually explain a deep learning neural network? Well, so of course, there are a lot of efforts underway
about inducing these parallel systems, be it on a per decision basis or otherwise, that will give you some what I was calling explanation linearization. There is argument about you can use a neural network to induce a model that works really well given data that's not terrific for learning anything else with, and then you use a neural network to then synthesize additional things, and you can possibly learn a more explainable or at least a more suitable model that you can then use that would be better than what you could have induced otherwise. There's certainly also a lot of work being done on various ways of organizing your deep learning neural network such that there is meaning in the intermediate stages of the deep learning neural network, and that can still give you, and this is why I was going through the different levels, right? Attribute only, attribute use, model generation. I really don't think you're going to be able to get a model generation explanation out of a neural network. I don't think we're ever going to get to a tractable explanation for why was this neural network weight 36, 0.36, whatever your scale is, right? I don't think that's ever going to be possible in a way that's going to be meaningful. But I think we might be able to get to the point where we get an explanation that's good enough for, let's say, okay, the robot made a mistake. In what area of state space is this thing confined? Can we fix it in here without catastrophically forgetting the good stuff that we had elsewhere? Does that answer the question?
Yes, but
yes,
there's one small other additional question.
If
you, for example, vision, if you do a classification of objects in the real world is infinite.
Of course.
So how do you deal with that then?
Well, and I guess this speaks to the question that came up before about, how do you deal with if the thing coming in isn't even in your space of prior whatever, right?
I mean, in terms of explainability or understanding where it was based upon, if the input can give infinite form.
Well, you have to have some idea of what your application is going to give you, right? You're driving down the road and all of a sudden you see a spaceship. You're not really going to have you're going to have to do a triple take before you can figure out what you do at this point, right? Well, it depends. I mean, if you know what I mean, right? So you have to make some kind of assumption, and part of this bit of about these models being useful for introspection, or at least these characteristics of models being useful for introspection, is when the agent has some way of knowing, I think this is the right answer, but I really don't know, right?
Yeah, so that's the distinction between dealing with uncertainty and saying in terms of, okay, I'm this and this certain about this, so this time and this.
Right. Is there at what point do I go, help? I need a human, right?
Well, at least understand the risks of flying something.
Yeah. Definitely, and I'd argue that the selection of machine learning technique or meta technique that you put over the top of it, that this kind of terminology suggests is also useful for filtering in or filtering out the types of techniques that are going to give you that kind of information.
So I'm sorry, but that's the remaining questions for the panel discussion, and now let's listen to the presentation by Raymond.
Okay, thank you.